Hi everyone, so I want to walk through an example similar to some of the homework problems that you have from section 1.3. So let's pick up from where we left the lecture today, and let's say we're looking at the Ebola outbreak data set over from 2014 to 2015. And in class, we estimated the average rate of change from t equals 100 to t equals 200. Let's say we want to find and interpret the meaning of the average rate of change over the interval from t equals 200 to t equals 250. So let's mark those 2 points on the graph. So at 200, we would be located right about here, and at 250, we're located right about here. And so the coordinates of the point at 200, well, we know that x is 200. We can approximate the corresponding output value from the graph. So here, answers might vary. That's okay, but approximately they should be similar. So I'm going to approximate the number of confirmed cases 200 days into the outbreak as 5,000. And for this point, we have a t-value of 250, and here we can approximate this as somewhere between 12,000 and 10,000, so we can approximate that as 11,000. So first, I need to identify the coordinates of the initial point and the end point of this interval. So I need to know the coordinates at t equals 200 and at 250. And these, from a graph, the best that we can do is approximate. If we're actually given a numerical table of values, then we can calculate this more precisely. And so the average rate of change, this is going to calculate the change in y values, in this case that's c, and we're going to divide that by the change in time, the number of days. And when we calculate this ratio, what we're actually going to calculate is the slope of the line connecting those two segments. So the slope, again, of the line connecting these 2 points is graphically how we can picture the average rate of change. So I can see that this slope is positive. To calculate this exact value more carefully, what we can do is take the change in cases and divide that by the change in time. So I can take my endpoint, so over here, this is like my T1 and my C1, so I can start with the end number of confirmed cases. So that would be this $11,000, or excuse me, 11,000 cases. And we're going to subtract from that the value, the number of cases at the starting point, which was the 5,000. So on the numerator, notice I have change in cases. And then in the denominator, we're going to take a look at the corresponding change in time. So here I start with the same point, the end point, and that had a t-value of 250. And then the t-value of the initial point was at 200. So taking the difference on top, this gives us a change of 6,000 cases. So overall, the total change in cases was about 6,000. So that's this vertical distance right here on the graph in green, and then the change in time is the 50 days. So that's this horizontal distance over here. And so we take this 6,000 and then we divide it by the change in time, which we now found to be 50, and this comes out to a total of 120, and the units here are cases per day. So just to review the steps that we took here, we wanted to find the average rate of change over this period from 200 to 250. So first, we find the coordinates of the start point that we got over here. We approximated this value, the output, at this point from the graph. Then we identified the coordinates of the end point of this interval at 250. So when t is 250, we approximated the output as 11,000. And then we take a look at what is the change in the total number of confirmed Ebola cases. So that's going to be this 11,000 minus this 5,000. That was this distance of 6,000. Then we looked at the change in time, which was this 50-day period. And then we look at these 6,000 cases over a 50-day period. That averages out to 120 cases per day. So this average rate of change, visually speaking, we can picture it as the line segment, the slope of the line segment connecting those 2 points. And so the last thing I want to discuss is how we could interpret the meaning of this value. And so we're going to interpret this similar to how we interpreted slopes. This is a certain type of slope. But when we were dealing with linear models, the rate of change, the slope, was the same over every interval. So we didn't have to specify over what interval of inputs are we looking at. With an average rate of change, since the slope of this graph is changing depending on what interval we're looking at, we should begin our explanation by specifying what period of time are we looking at. So over here, I have over the interval from t equals 200 to t equals 250. So now I've specified we're looking over this interval of time. And the next thing I need to do is, well, what is happening over this interval of time? And so this part of the explanation is going to be very, very similar to how we explained interpreted slopes. So over this interval of time, the number of Ebola cases is increasing by 120 cases per day. So notice the units of the average rate of change are the same as the units of slope. But the one thing that we want to change is that the slope is not the same over this interval. So sometimes it's flatter, at some points it's steeper. And so this 120 is not a constant rate, but it's telling us on average how much the number of cases have gone up each day. So for some days, there were less than 120 new cases. On other days, there were more than 120 new cases. So here we should add in here the fact that this is not a constant change every day, but in fact, this would be an average change over this period of time. So we calculated the average of change the same way as we calculated slopes. We interpret it very similarly, but we need to, one, take into account the period of time that we're looking at, and two, we need to be sure that we clarify this change is not a constant change, but an average change. So hopefully this gets you a nice similar example to help you out for the homework problems on 1.3.